Hello everyone, my name is Çağlar Demir. I am a research fellow at the Data Science Group of Padova University. Today, I am pleased to present a method based on Kronecker Decomposition to reduce the number of parameters in an embedding model while retaining its effectiveness. This work is done by collaborating with Julian Linian and Axel Ngonga. Knowledge graph embedding research signals an ever-increasing effectiveness on benchmark datasets. Yet, behind the scenes, hyperparameter optimization plays an important role in this impressive progress. Unfortunately though, as the size of the knowledge graph grows, training and optimizing an embedding model becomes computationally challenging, sometimes even infeasible. Consequently, reducing the size of an embedding model without decreasing its effectiveness plays an important role in many applications. In this work, we design a method based on Kronecker decomposition that allows us to reduce the explicitly stored parameters significantly with no cost in effectiveness. Before diving into details, I would like to swiftly go through the preliminaries. A knowledge graph can be defined as a set of triples. A knowledge graph embedding model aims to map a knowledge graph into a d-dimensional continuous vector space while preserving the input's inherent structure. Finding a good ratio between expressiveness and the parameter efficiency is a keystone in many successful applications. As the size of the knowledge graph increases, the importance of parameter efficiency becomes more tangible. Knowledge graphs used in real-world applications contain millions of entities and billions of facts. This gigantic size introduces various different challenges. In this work, we aim to design a model that alleviates these challenges. So on the right hand side you can see imagine that we have billions of facts. We would like to design a model that allow us to compute embeddings with less memory requirement or decreases the memory requirement and ideally decrease also training time, and by these means we can perform hyperparameter optimization. Hadamard product elementwise vector multiplication or matrix multiplication plays an important role in many disciplines. For instance, most knowledge graph embedding models rely on this operation to capture the elementwise interactions between head entity and relation embeddings. Kronecker product, compared to the Hadamard product, performs a blockwise operation. This means that every element of the input operand, here in the equation 2 is x, interacts with every other element of the second operand, namely z. Let's put these two operands, two products in action within a standard baseline knowledge graph embedding model, namely this model. This model computes a score of a given triple by elementwise operations, Hadamard product followed by a dot product, as shown in equation 3. So, if the vector size is 2, we perform these operations and we obtain this scalar value on the right hand side. The important part is that after we compute the gradient, or the gradient of the loss with respect to the first item in the head entity, namely A, does not include information about the interaction between A and B, as well as A and A, so itself. And then there's no information between its neighboring or its other features in the head entity embeddings, as well as itself. Now we ask ourselves the following question: would it be possible to capture these interactions without increasing the parameter demand? And in fact, Kronecker product allows us to capture this information. For instance, in equation 5, we applied a Kronecker product on embedding vectors, and then we showed in equation 6 that the missing interactions, missing part that we just mentioned, captured in the middle term. And we argued that capturing these interactions would lead a more compact representations by means of encouraging the feature reuse. And ideally, this would allow us to retain the effectiveness of the model while using less parameters. To analyze this hypothesis, our conjecture, we design a two model. Here in equation 7, we apply Kronecker product only on relation embeddings. And important to note that scores of triples are still computed based on 3 d-dimensional embedding vectors. So although we store less parameters on relation embedding matrix, the whole embeddings of relations, we don't need to store the d columns, but we can store less. We don't need to allocate that amount of memory for the relation embeddings. Then we ask ourselves the following question: if we could do this, why wouldn't we apply this technique to the entities as well? And here we propose a KGE Challenges model where we apply the Kronecker product on head entity embeddings. We didn't include the Kronecker product on the tail entity embeddings because we would like to use the one versus all and k versus all training or k versus all training strategies, as these techniques lead to state-of-the-art link prediction performances or embedding performances in many downstream tasks. Obviously, there are many variations that we haven't explored during our work due to time and space complexities, due to the time and space constraints. But one could extend this idea to the equation 9, equation 10, as you can see. In our experiments, we used one versus all training regime, binary crest entropy, which is standard loss function used in the knowledge graph embedding research. We fixed the seed of random number generator to ensure the reproducibility of our experiments, and we conduct extensive hyperparameter optimization via grid search on embedding vectors to get the fine-grained performances, and we report the all result of the all grid search or variations or configurations. We use two benchmark datasets, and we use a standard metrics to see that if our model leads to more compact representations, we expect that our model will be more robust against noise. We also add this scenario, as well as we would like to see that model calibration, the impact whether this more compact representations lead calibrated results, calibrated predictions. Here we report our general results. So it clearly shows that applying the Kronecker decomposition leads significant reduction in the number of parameters, as shown in the theta. These results overall these results tells us that applying Kronecker decomposition on tail entities has a more impact than applying the Kronecker decomposition on relation embeddings only, to reduce the number of parameters in an embedding in the whole process. After these results, as I mentioned, we conduct a series of experiments, and here we report the average results. And this results indicates that on the noisy settings, the applying Kronecker decomposition on relation embeddings and tail entity embeddings still lead to better performance. To conclude our work and conclude this presentation, we propose the Kronecker decomposition for knowledge graph embedding models. This leads to significant parameter efficiency by means of feature reuse, and we developed a hardware agnostic framework we call DICE embeddings to allow the practitioners to apply embedding models on very, very large knowledge graphs with an ease. With this, I would like to thank you for your attention. And if you have any suggestion or any question, feel free to contact us. Thank you.